We are going to discuss about the elementary band theory of solids and subsequent exceptions for the Bloch theorem and chronic penny model. As we go on, the success of the free electron gas model in describing electrons in crystals, okay, it, it must be recognized that the assumptions of the one electron approximation and of a square well potential are oversimplifications. Thus, one cannot expect this model to explain, for example, the fundamentally important optical and electronic properties of semiconductors. If, if one imagines that a solid is created by allowing initially free electrons to gradually approach one another, then the discrete nature of the energy levels of the isolated atoms should clearly be reflected in the properties of the solid. Indeed, the discrete energy levels must be present in order to explain, such as the sharp resonance-like structures observed in the optical spectra of solids. An explanation of such features is beyond the scope of the free electron gas model. Furthermore, this model is unable to shed any light on the nature of semiconductors and insulators. To make further progress, one has to make into account that the electronic states in solids form so-called bands. So one can think of these as deriving from the states of the free atom. So in our present approximation, all derivations from perfect periodicity, be they static perturbations of the lattice or dynamic vibrations of the atoms, will be neglected. The assumption of an infinitely extended potential also means the neglect of all surface effects. To arrive at a finite crystal, that is, one with a finite number of degrees of freedom that is compatible with the infinite periodicity, one again makes use of the periodic boundary conditions, which is Born-von Laue periodic boundary condition. So to start with, the electron levels in a periodic potential and the general properties is, as we know, because the ions in a perfect crystal are arranged in a regular periodic array, we are led to consider the problem of an electron in a potential UR with the periodicity of the underlying gravities. That is, UR plus capital R is equals to UR. For all the gravities vector capital R, since the scale of periodicity of the potential U is at the order of Armstrong, is the size of the typical de Broglie wavelength of an electron in the Sommerfeld free electron model. It is essential to use quantum mechanics in accounting for the effect of periodicity on electronic motion. Right? So we will always focus that emphasize that the problem of electrons in a periodic potential does not arise only in the context of metals. Most of our general conclusions apply to all crystalline solids and will play an important role in our subsequent discussions of insulators and semiconductors. The problem of electrons in a solid is in principle a many electron theory problem. But the full Hamiltonian of the solid contains not only the one electron potentials describing the interactions of the electrons with the massive atomic nuclei, but also pair potentials describing the electron-electron interactions. In the independent electron approximation, these interactions are represented by the effective one electron potential U. The problem of how best to choose this effective potential is a complicated one, and we merely observe that whatever detailed form the one electron effective potential may have, if the crystal is perfectly periodic, it must satisfy the periodic boundary condition, that is the periodicity of the crystal potential as UR plus R is equals to UR. So from this fact alone, many important conclusions may be drawn. Qualitatively, however, typical crystalline potential might be expected to have the form shown in the figure, resembling the individual atomic potentials as the ion is approached closely and flattening off in the region between ions. So this is the picture of a crystalline periodic potential plotted along a line of ions and along a line midway between plane of ions. Closed circles, these are the equilibrium ion sites. The solid curves, these black lines, give the potential along the line of ions. The dotted curves, this wave nature of the dotted curves, give the potential along a line between planes of ions, and the dashed ones, right, give the potential of single isolated ions. As we all know from the higher secondary physics, that potential energy is always inverse square type, or Vr is proportional to 1 upon R, then the potential dependence upon the radial content always goes as the rectangular hyperbola. So if these ions situated as static and the rectangular hyperbola type behavior of R versus Dr, this type of behavior can be obtained, and from this the effective potential would be look like this, the black ones. So we are just left to examine the general properties of the Schrodinger equation for the single electron as h psi is equals to minus h cat square by 2 grad square plus ur psi is equals to E psi. That follows from the fact that the potential U has the periodicity of the lattice, and the free electron Schrodinger equation without the potential term, okay, we assuming that there is no interaction between the electrons, is a special case of this Schrodinger equation. Okay, so independent electrons, each of which obeys one electron Schrodinger equation with a periodic potential, are known as the Bloch electrons. And in contrast to the free electrons, to which the Bloch electrons reduced when the periodic potential is identically zero. The stationary states of Bloch electrons have the following very important property as a general consequence of the periodicity of the potential. Furthermore, if we go on, the distinction between the resistivity values of the conductor's superconductivity apart, the insulators is striking. The resistivity of a pure metal at low temperature may be of the order of 10 to the power minus 8 ohm centimeter, and the resistivity of a good insulator may be as high as 10 to the power 22 ohm centimeter. So we can now notice that the difference between the insulators and the conductors, only by extending the free electron model to take into account of the interaction of electrons with the periodic lattice of the solid. So we shall encounter some quite remarkable properties possessed by electrons in crystals. They may respond to applied electric or magnetic fields as if the electrons are endowed with an effective mass m star. which may be larger or smaller than the free electron mass, or may even be negative. Further, there are situations in which it is convenient to attribute to the charge carriers in crystals a positive charge plus a modulus of electronic charge. We denote such carriers as holes in contrast to electrons which behave with their normal negative charge, that is minus modulus of E. Students with no familiarity with the ideas of quantum theory will have some difficulty with the present scenario. So on the free electron model, the allowed energy values are distributed quasi-continuously from 0 to infinity, and the dependence of E is h cut square by twice m kx square plus ky square plus kz square, where for a cube of side L, this kx, ky, and kz takes the value of 2 pi by L times 0 plus minus 1 plus minus 2 plus minus 3. And the free electron wave function are of the form psi nearly equals to e to the power I k dot r and represent running waves carrying momentum p is equals to h cut k according to the de Broglie relation. Okay, we have already seen that the X-ray and the elastic wave propagation in crystals, that Bragg reflection is an important and characteristic feature of wave propagation in periodic structures. Bragg reflection occurs also for electron waves in crystals. The observation of Davison and Germer on the wave nature of the electron were observations of the Bragg reflection of an electron beam from the crystal surface. The most important consequence of Bragg reflection for our present discussion is that it leads to the existence of the energy gap in the distribution in energy of the states of the conduction electrons. That is, there may arise a substantial region of energy in which solutions of the wave equation do not exist. Such energy gaps, or forbidden energy bands as they are also called, are of decisive significance in determining whether a solid is to be an insulator or be a conductor. The solid will be an insulator if all the energy levels below a forbidden band are filled with electrons, with all levels above the forbidden band are vacant. I repeat, the solid will be an insulator if all the energy levels below a forbidden band are filled with electrons and all levels above the forbidden band are vacant. So let us now try to understand physically the reasons for the existence of forbidden band, considering first the simple problem of the monoatomic one-dimensional lattice. The low energy portions of the band structure, as shown in the figure, for free electron, for entirely free electron, and this is for electrons which are nearly free, but which have an energy discontinuity at k is equals to plus minus pi by a, giving rise to a forbidden energy band. So in one dimension, the Bragg equation 2d sine theta is equals to n lambda, right? Becomes k is equals to n pi by a. So the first reflection occurs at k is equals to plus minus pi by a, and the first energy gap also occurs at these points. Other energy gaps occur for the other positive and negative integral values of n. The reflection at k is equals to plus minus pi by a arises because the wave reflected from the p plus minus 1th atom interfaces constructively with the original wave at the pth atom. The difference in phase being just plus minus 2 pi for these particular values of k. The region in k space between minus pi by a to pi by a, right? This region is referred to in the instance as the first Brillouin zone. So the energy is quasi-continuous within a Brillouin zone and may be discontinuous on the boundaries of a zone. The energy is quasi-continuous rather than continuous within a zone because of the imposition of boundary conditions on the problem. So at k is equals to plus minus pi by a, the stationary state wave functions are not traveling waves but that of a standing wave for the free electron module. But the solution at these particular k values are made up equally of waves traveling to the right and to the left. They are standing waves. It is really obvious that the solution when the Bragg condition is satisfied cannot be in the form of traveling waves. For a wave traveling in one sense is soon Bragg reflected and then travels in the opposite sense. The next Bragg reflection reverses the direction of travel again. The only stationary situation is that represented by standing waves. So in the lowest approximation, we have k is equals to plus minus pi by a. The two independent standing wave solutions, psi1 is equals to sine pi x by a, which is e to the power I by x by a minus e to the power minus I by x by a, and psi2 is equals to cosine pi x by a, which is e to the power I by x by a plus e to the power minus I by x by a. So both these solutions hold equally at k is equals to plus pi by a and also at k is equals to minus pi by a. The solutions are both made up, as can be seen from the right hand forms of equal parts of wave traveling to the right and to the left. So we must show that the two solutions psi1 and psi2 correspond to different values of the energy, even though the functions have the same values of the wave vector. So in this figure, we have indicated that general nature of the variation of the electrostatic potential energy of a conduction electron in the field of the positive ion force of a monoatomic linear lattice. We expect the ion force to bear a positive charge as each has lost one or more valence electrons in forming the metal. In the following figure, the sketch of the distribution of charge density corresponding to the standing wave psi1 and psi2 and to the plane traveling wave. We note that the traveling wave e to the power ikx distributes electronic charge uniformly over the line with the origin, and the standing wave psi1 nearly approximately equals to sine pi x by a distributes charge preferentially midway between ion force, and the standing wave psi2 cos cosine pi x by a distributes charge preferentially on the ion force where the potential energy is a minimum. So on calculating average values of the potential energy over the three charge distributions, we expect to find the potential energy psi2 less than that of the plane wave, while the potential energy of psi1 is greater than that of the plane wave. So if the potential energy of psi1 and psi2 differ by an angle delta E, we have referring to this figure an energy gap of width delta E. The wave function at point A will be psi2 and the wave function above the energy gap of point B will be psi1. As shown in this figure, right? I repeat, if the potential energies of psi1 and psi2 differ by an amount delta E, which is the forbidden band gap, an energy gap of width delta E, the wave function at points A will be psi2 and the wave functions above the energy gap at point B will be psi1. So far, we have completely neglected the effects of the ion force on the motion of the valence electrons. We consider valence electrons to be those outside of a closed shell configuration, so that sodium has a single 3s valence electron outside, magnesium has two 3s electrons outside, gallium has 10 3d electrons, two 4s electrons, and one 3p electron outside. The s and p electron are usually considered as the valence electrons, since they are responsible for bonding. Sometimes the mixing of d electron atomic states with valence electron states is important. To get some idea about the nature due to the ion course, let's consider the simple case of an isolated sodium plus ion. The ion has charge plus E and attracts an electron via the Coulomb potential Vr is equals to minus E square upon R, where R is greater than the ionic radius. So for a pair of sodium atoms separated by a large distance, each conduction electrons, that is 3s electron in sodium, has a well-defined atomic energy level. As the two atoms are brought close together, atomic potential Vr begin to overlap. Then each electron can feel the potential of both ions. This gives rise to splitting of the degeneracy of atomic levels. For a large number of atoms, the same effect occurs. Think of a crystal structure with a nearest neighbor separation of 1 centimeter. The energy levels of the system will be atomic in character. However, as we decrease the nearest neighbor separation, the atomic energy levels will begin to broaden into bands, right? So the equilibrium separation of the crystal is the position at which the total energy of the system is minimum. Let me draw, show you out this scenario. Okay. Okay, this is the figure when we decrease the nearest neighbor separation, the atomic energy levels will begin to broaden into bands. The equilibrium separation of the crystal is the position at which the total energy of the system is minimum. In all crystalline solids, the electronic energies form bands as allowed energy values separated by energy gaps, bands of forbidden energy values. These energy bands determine the electrical properties of the solid. This is the Coulomb potential in a bound state structure, R versus here, and here, as we have already discussed, the atomic levels form a band like this way, rather than a single line. So this is the illustration of the energy band formation in case of semiconductors and insulators. As we go on from this to okay, so as we discussed in case of free electron theory, we assume that the electrons move in a region of constant potential inside one or three-dimensional potential well. Although the free electron theory is able to explain the phenomena such as electrical conductivity, thermionic emission, etc., it fails to explain why some materials are good electrical conductors while some are good electrical insulators, and still some others are semiconductors. So in order to understand the difference between the conductors and the insulators, it is necessary to incorporate the variation of the potential inside the crystal due to the presence of the positive ion course in the free electron model. It appears realistic to assume that the potential inside a metallic crystal to be periodic with the periodicity of the lattice, somewhat as shown in the figure, this figure, when V tending to infinity, the surface potential is at the form of 1 upon R. The potential is minimum at the positive ion force, right? Potential is minimum and maximum between the two ions. The corresponding one-dimensional Schrodinger equation can be written as okay, this one d2 psi dx square plus 8 pi square a over h square e minus bx psi is equals to 0, where the periodic potential Vx may be defined by means of the lattice constant A as Vx is equals to Vx plus A, employing the periodic potential. The Bloch has shown that the one-dimensional solution of the Schrodinger equation takes the form psi x equals to e to the power ikx ukx, and in 3 dimensions this takes the value of psi kr is equals to e to the power ik dot r ukr is known as the Bloch function in 1 and 3 dimensions respectively. They represent the free electron wave, that is e to the power ikx and e to the power ik dot r, modulated by the periodic functions ukx and ukr, where ukx and ukr is periodic with the periodicity of the lattice in 1 and 3 dimensions respectively. Therefore, considering only the one-dimensional case, and suppose if we have n, if n is even number of atoms in a linear chain of atoms of length L, then we can write ukx is equals to ukx x plus na, and depends on the exact nature of the potential field. These two equations becomes psi k x plus na is equals to uk x plus na to the power I k x plus na, which is the expression is like that. And if the periodicity happens, this turns out to be psi k x to the power I k na. So this is frequently referred to as the Bloch condition. Similarly, the complex conjugate will be written as psi k star x plus na is equals to uh, e to the power minus I k na psi k star x, and psi k x plus na psi star psi, that is, and the product of psi k star x plus na is equals to psi k x times psi k star x. So this indicates that the probability of finding the electron in same everywhere in the whole chain of atoms. That is, it is not localized around any particular atom, but is shaded by all atoms in the chain, the whole crystal in 3 dimensions, which gives, if this is equal, this is being equal for the periodic lattice, my this term e to the power ikna should be 1. So this will true only if from mathematics that k, if the I times the quantity, that is kna is equals to 2 pi times any integer value. We assume this integer as small n, then kna is equals to 2 pi n and k is equals to 2 pi n by capital Ma, which is 2 pi n by L, where n is equals to 0 plus minus 1 plus minus 2. And capital L is the length of the chain of atoms. When n takes the value of capital N by 2, we have k wave vector is equals to pi by 2, which is the age of the first biloazole. So when L is very large, that is the length of the chain of atoms are large enough, then what happens? N is also large, and the allowed values of k would come close together, and their distribution along k-axis becomes quasi-continuous. The total number of allowed k values in the first Brillouin zone would be length of the first zone divided by length of the unit spacing, that is 2 pi by a over 2 pi by L, that is L by a is equals to n, which is that is the equal this is equal to the total number of atoms in the chain of atoms or in the unit cell in these dimensions. So let us now introduce the translation operator. because the crystalline potential seen by a single electron in a solid is a periodic function of position with the period of the lattice. So if the translation operates on the function, it gives the same function with the periodicity of the lattice. So it is useful to introduce the translation operator, that is capital T, and fx is an arbitrary function of position and a is the period of the lattice. So it is clear that the T commutes with the single particle Hamiltonian H, which has the kinetic term only. There is no kinetic and the potential term, where the potential term has the periodicity of the lattice. Because we get x prime is equals to x plus a, we can see that del x prime is equals to del x and px prime is equals to px. One of the most useful theorem of linear algebra for the study of quantum systems states that if two operators commute, one can find common eigenfunctions for them. That is, they can both be diagonal in the same representation. Let phi be the eigenfunction of capital H and T, right? So H psi is equals to E psi, and simultaneously T psi is equals to lambda psi, where E and lambda are the eigenvalues. Clearly applying T to psi n times gives T to the power n operating upon psi x is equals to lambda to the power n psi x, that is psi x plus na. If we apply periodic boundary conditions with the period capital N, then psi x plus na is equals to psi x. This implies that t to the power n operating upon psi x gives me the same wave function back. Or comparing these two, we have lambda to the power n is equals to 1. Thus, lambda itself must be the nth root of the unity, that is lambda is equal to e to the power I 2 pi by capital N times small n, where n takes the values of the integer 0, plus, minus 1, so on and so forth. And we can write lambda as e to the power I k a, where k is equals to 2 pi by capital N small a times small n. Then it is apparent that two values of the k which differ by the 2 pi by a times an integer give identical values of lambda. As usual, we choose the capital N independent values of k to lie in the range minus pi by a less than k less than equals to pi by a, the first Brillouin zone of a one-dimensional crystal. So for more than one dimension, T suffix r is the translation operator, that translates through a lattice vector capital R, gives me the value TR operating upon psi r e to the power I k dot r psi r, where capital K is equals to 2 pi by n, n1 b1 plus n2 b2 plus n3 b3, where n1, n2, n3 are integers and b1, b2, b3 are primitive translations of the reciprocal lattice. We have assumed a period capital N for periodic boundary condition with L1 is equals to NA1, L2 is equals to NA2, and L3 equals to NA3, and values of N1, N2, N3 are chosen to restrict K to the first Brillouin zones. Then let me introduce the Bloch theorem. We have just demonstrated that for a one-dimensional crystal with capital N atoms and periodic boundary conditions, T psi x is equals to psi x plus a is equals to e to the power I k a psi x, where the n independent values of k are restricted to the first Brillouin zone, and we can define a function ukx e to the power minus ikx psi x, and it is apparent that t operating upon ukx is equals to t to the power minus ikx psi x, that is e to the power minus ik x plus a psi x plus a, which is e to the power minus ikx psi x, and which is ukx. Therefore, we can write psi x is equals to e to the power ikx ukx, where ukx is a periodic function, that is ukx plus a is equals to ukx. This is known to physicists as Bloch's theorem. Although it had been proven some time earlier that Bloch and is known to mathematics as Foucault's theorem. So depending upon this, we can calculate the energy bands. These are two very different starting points from which one can approach energy bands in solids. The first approach is to start with atomic orbitals and to form linear combinations which satisfy Bloch's theorem. The second is to start with Sommerfeld free electron gas and to see how the periodic potential of ions changes. The Ek is equals to h cut square k square by 2 m free electron dispersion. The first approach works well for the systems of rather tightly bound electrons, while the second works well for the weakly bound electrons. We will spend a good deal of time on the nearly free electron model and how group theory helps to make the calculations easier. Before doing that, we begin with the first approach called the tide binding method, or the LCAO, linear combination of atomic orbitals, from the next class. We go on. So thank you.